Hello, how are you doing? Mohammed Porgaz here with another lecture on concrete mixture design and proportioning. Today we will cover steps 3 and 4. We discussed in the previous video that there are 10 steps to concrete mixture proportioning, and we already have covered 2 of those steps. Today we will cover, in this video, we will cover steps 3 and 4. Now, let's get started with step 3, selecting the maximum aggregate size or maximum size of aggregate, however you're comfortable with it. So, what information do we need in selecting the maximum size of aggregate? Sometimes this information is provided directly to you in the case of the example, for example, that we are solving in this series of lectures, that the maximum size of aggregate is given to you. And sometimes the dimensions and the application of the concrete is given to us. For example, if the concrete is used as a slab, let me just get this down over here. All right. For example, if the concrete is used as an on-grade slab or slab on grade, we want to make sure that the maximum aggregate size, our maximum size, MSA means maximum size of aggregate, is less than 1/3 of the depth of the entire slab. In the case of the concrete that is being placed inside the form, we want to make sure that the maximum size of aggregate is smaller than 1/5 of the dimensions of the distance between the form, or it is smaller than 3/4 of the size of between the reinforcing bars, and of course the size of between the reinforcing bar and form. So for those two we use 3/4. Maximum, basically 3/4 of an S. S can be this or this one. The reason is that we want to make sure that these aggregates are flowing inside our form and they are placed without causing any bug holes or any areas that concrete cannot flow to. Now, some of you will be wondering, why do we even need to consider maximum size of aggregate? Why don't we use a very small aggregate? Then in that case we don't have to worry about step number 3. The reason is that we want to use the largest aggregate possible for economy and durability of our concrete mixture. That is shown over here. On x-axis you see the maximum aggregate size in inches, and on y-axis you see the percentage of the total volume. We have aggregate and we have paste content. And at this point of the semester you already know that paste is a mixture of cement and water. Now, we see over here, as the maximum aggregate size increases, the amount of paste inside our concrete is decreasing. The percentage of the paste is decreasing. Again, paste is made of the cement, and it is the most expensive component of the concrete, so we want to make sure that we use less of that for economy. And of course, a lot of the durability problems associated with concrete are associated with the paste phase. And for that reason, we want to make sure that we have as little as possible paste, cement paste inside our concrete as possible. Another reason is that the cement paste has to coat the entire aggregates. And the smaller aggregate that we use, the larger surface area that we have, therefore we need to use a little bit more paste content. For example, over here it's schematically shown that we have a cube of dimensions D. All the dimensions are D over here, therefore the surface area is 6D squared. You can use very complicated mathematics to figure that out. And if we reduce the size of that aggregate, for example, if we break all of the dimensions into half, suddenly we see that the total surface area has increased. Therefore, we need more paste to be able to cover all of those surface areas. Therefore, we always want to put the largest aggregate possible inside our mixture. Of course, maximum aggregate size has also impact on the proportioning of the proportions of the mixture. Again, over here we can see that water and cement make the paste content of our mixture, and as the maximum aggregate size increases, the amount of paste inside our mixture also decreases. And the amount of aggregate of a volume percentage of the aggregate increases. And of course, aggregates have other influences on influences on our mixture as well. For example, in some cases we want to use a smaller aggregate because of the durability concerns with the so-called decracking. I'm not going to get into the detail of that, but in certain cases we want to use a small aggregate, but in general larger aggregates we want to use for economy and also to reduce the shrinkage. Now, why it is important for shrinkage? The reason for that is that the main phase that shrinks inside the concrete is the cement paste, and we want to reduce the amount of shrinkage inside the concrete. We want to reduce the amount of paste, and one way to do that is to increase the aggregate size, which will translate into increasing the volume percentage of aggregate. All right, in our particular example, we are solving an example. Remember this red ribbon over here? We are solving an example over here. In this particular case, the maximum size of the aggregate is given to us as 1.5 inch. So this step of the example is very, very easy. We're going to go over here to step number 4, estimating water and air of our mixture. Now, the basic idea is that there are basic trends. There are relationships or trends between water content, slump, and aggregate. We already talked about the slump, how to select the slump from a table that is suggested by ACI, and we talked about the aggregate size, how to select your aggregate size based on the application and the dimensions of the form or slab on grade. Now, we want to select the water, estimate the water and air, and ACI provides tables for this, and this graph on the right over here is made based on those tables by ACI, and I will talk a little bit more about this graph in a few slides. So again, we talked about this. We said that we want to use aggregates that are larger. The reason is that the larger aggregate we have, the less surface area we have. For example, if we want to consider cubic foot and we want to fill these with spheres, they are all spheres and they are the same identical size, and we want to use we want to calculate the surface area of this. You can see over here on x-axis we have the aggregate size or the size of the sphere, and on y-axis we have the surface area of the spheres in inch square. On x-axis on top, the same information about the aggregates or spheres in this case is provided, but they are in millimeter. And you can see that as the size of these spheres decrease, the surface area of the spheres exponentially increases over here, and of course this is a model for aggregate, and the smaller aggregate we have to use a lot more paste to cover the entire surface area. All right, so let's talk about these basic trends that comes from ACI table. On x-axis you see the desired slump in millimeter. On x-axis on top you see exactly the same information, desired slump in inches. And of course, 1 inch, we know it is 25 millimeter, and 8 inch is 200 millimeters. So it is exactly the same amount, same information provided. On y-axis on the left, we see the base estimated water content in kilogram per cubic meter. And on y-axis on the right, we see the same information in pound per cubic yard. So whichever of these units systems you are more comfortable with, you can use this table for. Now, the first trend that we observe over here, for a given aggregate size, for example, I'm going to go ahead and choose 25 millimeter aggregate size over here. We see that we see that to have a higher slump, we have to use more water. So if we want 1 inch slump, we use 170 kilogram per cubic meter of water, kilogram per cubic meter of water. And if we want 8 inches of slump, we have to use a lot more. We have to use something around 195 kilogram per cubic meter. So the idea is that when we increase the water, the slump increases, or if we want more slump in our concrete, we have to use more water. So that is pretty intuitive. A second idea, the second trend that you observe over here is that for a given aggregate size, let me, if I can speak today, for a given slump over here, depending on the aggregate size, we need different amount of water. That's a very complicated way of saying something very simple. For example, if we have 2-inch aggregate size, 50 millimeter, we would require something around 275 pounds per cubic yard of water to achieve 4 inches of slump. Now, this line has to be a little bit more straight over here, but you probably get the point. 275 pounds per cubic yard of water we need to add. 275 pounds per pound of water per cubic yard of concrete. Now, if we have 9.5 millimeter or 3/8 of an inch, in that case, we need to add something around 400 pounds of water per cubic yard of concrete to achieve the same slump, the same 4-inch slump of the concrete. Now, again, the reason for that is that as the aggregate size decreases, we have a lot more surface area that we need to cover with cement paste, and for that we require a lot more water. So this is the idea. So there are 2 major trends that are shown with these arrows over here. The more slump that we need, the more water we need to add. And if the aggregate size is smaller, we need to add a lot more water to the system. All right, let's go to our particular example over here. We said that we are given 1.5-inch maximum aggregate size. And we said that in our particular example, we will go ahead and select the 6-inch slump. And we will drop a line over here from 6-inch. In this slide, the lines are straight, as opposed to the previous slides that I was trying to draw them and did not succeed. And then we draw a horizontal line, and we see that to achieve a 6-inch slump with 1.5-inch aggregate size, we need something around 300 pounds of water per cubic yard of concrete. Something around 300 to 305. Now, we estimated water. And, however, I have to tell you that this is wrong. We talked about the water. We did not talk about air. So I intentionally put this is wrong over here because this is wrong for this particular example. Before we completely and correctly solve this example, I would like to talk a little bit about air. Now, the basic trends that we saw, that we use in that particular table, comes from a concrete that has no air entrainment. This is a table from ACI 211, and we can see, for example, for 6 to 7 inch of slump, for an aggregate size of 1.5 inch. At 1.5 inch over here, if we drop a line from both sides, we get something around 300 to 315 pounds of water per cubic yard of concrete. And this is what we saw in the previous slide. In that particular case, there is some entrapped air, mainly because of the mixing process inside the concrete. There is some entrapped air inside the concrete that accounts for something around 1% of the total volume. This table that you can see on this slide, again, it is for no air entrain, no air entrainment or non-air entrained concrete. In this particular case, all of the information are exactly identical to the previous slide. They are just provided in metric unit. Now, if you look at the same table for concrete that has air entrainment in it, these numbers are slightly different. And then we have air content for different exposure conditions. You may recall that in our particular example, we had a reinforced concrete beam that was exposed to moderate exposure. And in a second, I will talk about what these different exposures are. But in this particular case, you can see that for 6 to 7 inches of slump, for 1.5-inch aggregate size, the amount of water that is required is different. It is 290 pound of water per cubic yard of concrete. And also, we need 4.5% air, which is really by total volume of the concrete, but the air will sit inside the paste, and that is a key for durability. So we want to intentionally introduce a little bit of air into our concrete. And why do we want to do that? So this is, and I will talk about why we need a little bit air inside the concrete. This is exactly the same table as I showed in the previous slide. This is only in metric units. All the information are provided in millimeter. Now, here are the exposure conditions. We have 3 different exposure conditions. They are called mild exposure or moderate exposure and severe exposure, and sometimes they are referred to as F0, F1, and F2 to identify these. So F1 or mild exposure is an exposure that our concrete during the service life is not exposed to freeze and thaw cycles. It is not exposed to de-icer. So in this particular case, you already know that bridge deck concrete is not F1. For example, a bridge in North Carolina or bridge in New York will be exposed to freeze and thaw and will be exposed to de-icer salt. So in this particular exposure, if air is considered, it is mainly for workability, and I will talk about why it increases the workability in a second. It is the air that is considered mainly for workability. It is examples of that. You can consider concrete that's indoor or outdoor in a mild climate. Okay, moderate exposure, which we are using in our particular example, is the exposure that there is no direct application of de-icers. Freeze and thaw is expected. For example, this can be a driveway, of a residential house that there is no direct application of de-icer, but freeze and thaw is expected. Occasional exposure to moisture before freeze and thaw, of course. These examples of that are beams, girders, and so forth in nice environment. Severe exposure is the worst type of exposure, that is continuous exposure to water before freeze and thaw. Bridge decks are examples of these. Pavements are examples of this. Concrete can be saturated in this particular case because of a lot of rain and water sitting at the surface of the concrete, and exposure to de-icers is expected. So really, these are the definition of the 3 types of exposure that we have. Now, why do we need air inside the concrete? First, let's consider concrete that does not have air entrainment in it. This is a concrete without air entrainment. And we will consider a concrete that has a degree of saturation bigger than 92%. And why that is important, it is because when ice forms inside the concrete, ice will start to expand. And when ice starts to expand, it will start to produce basically tensile stresses inside our concrete. Now, however, in concrete material, we need for the concrete to be something around degree of saturation of 92%, and I will tell you that 92% is not an exactly correct number. It turns out that it is something around 88%. However, the idea is that if we don't have a lot of water inside the concrete, we don't worry about the freeze and thaw. If the concrete is completely dry, no ice will form through it, in it, and therefore there is no freeze and thaw durability issue. But if concrete has enough water in it, let's say something around 92%, for simplicity in this particular case, and ice starts to form, ice will start to expand. However, ice does not form in concrete at 0 degrees C. This is because we have a lot of salts inside the concrete. Concrete pore solution is really very similar to saturated calcium hydroxide, so it does not freeze at 0, and there are other effects due to the size of the pores inside the concrete. And if these effects will drop down or depress the freezing point. Now, if we have a concrete that has a degree of saturation of 92%, concrete that has been exposed to a lot of water and has been saturated above 92%, when the temperature drops down, the ice will start to form inside the system and will start to expand, and will result in cracking of the concrete. Now, we all know that the concrete material is not very good does not have a very high tensile strength, and these formation of ice will start to produce tensile stresses inside the concrete and will cause cracking. Now, what happens if we have air inside the concrete? Now, if we have air inside the concrete and these air voids are air-filled pores inside the system, we see that when the temperature drops down, these air voids will in fact work as a shock absorber. The water will move inside this, will form ice inside them, but it has enough space for the ice to form, so it will not produce tensile stresses inside the system. For example, over here we see that when the temperature goes to -5°C, the water will start to move toward these air voids, and even if you drop the temperature lower, the water will start to expand inside these pores, the ice will start to form inside these air voids, but there is enough space inside the system that the cement paste will not crack. And of course, as the temperature goes back up, the water moves back to the capillary porosity of the void of the cement paste. So these air entraining pores that I have identified with AE over here, they basically protect the cement paste from cracking due to formation of ice inside the system. Remember that we talked about the mild exposure, and we said that in mild exposure, mainly air is there for workability. It turns out that the air bubbles that form inside the concrete, they are spherical. We all probably know that at this point. And they act basically as a lubricant inside the system, the so-called ball bearing effect, for example. They start to separate surfaces of cement paste from each other. Over here we see a cement paste that does not have air entraining agent, and a cement paste, the surface of the cement paste that has air entraining agent in them. And these will start to separate these cement paste particles, and they will start to let them slide on top of each other very easily, and that will increase the workability of our concrete. All right, how much air do we need inside a concrete? It really depends on the type of the structure. We talked about this, exposure condition and climate condition and type of the structure. Freeze and thaw, how many freeze and thaw are you expecting? Now, do we have extended exposure to de-icer and to de-icer salt? And what is the design life of the concrete? And in general, we will talk about this, water cement ratio of the concrete should be less than 0.45 when we are expecting freeze-thaw exposure. But on x-axis over here, you see the maximum aggregate size. On y-axis, you see the total air content. And you can see that when we have different type of exposure, as the exposure becomes severe, more and more air needed inside the concrete. For example, over here for for a certain aggregate size, we can see that as we move from mild to severe exposure, we need a lot more air inside our system. And generally, we see that as the maximum aggregate size increases, the amount of total amount of air inside the system, required air decreases. This is because the total amount of paste decreases inside the system. And the airways are there to protect the paste. We have lower amount of paste as the maximum aggregate size increases, therefore we need a little bit lower air inside the system. We are at the example slide over here. In this particular case, we talked about a maximum aggregate size of 1.5 inch for our application, and we said that we would consider a 6-inch slump, and we see that we end up with 290 pound of water per cubic yard of concrete. Now, we said that the exposure of a concrete beam is moderate exposure, 4.5. I will go ahead and consider 5.5% air inside this. Now, the main reason that I am doing is there is no correct, there is no wrong. I shouldn't say that. It is not. It will not hurt if you consider a little bit more air inside the system, because if you consider a little bit more air inside the system, it will be a little bit more conservative with regard to durability, and it will not hurt the mixture. Now, generally, here are a little bit guidelines for you with regard to the amount of water and air. We generally need to provide the limit for the amount of air. For example, if for example design says 5.5% air we would require, it would be a good practice to generally specify a range of 5 to 7%. You don't want to specify too low. The rule of thumb, ROT over here, is that minus 0.5% plus 1.5% is a good range. That will provide an overall 2% variation. For example, in the case of 5.5, we want to specify 5 to 7, because providing 5.5 will be a little bit challenging for mixture producer. What if they get 5? What if they get 6? So providing a range is a better practice. Do not specify more than 9%. Remember, I will tell you another rule of thumb here. For every 1% of air, the compressive strength F prime C will decrease 5%. So this is very important. You do not want to specify a lot of air inside the concrete, because you will run into other issues, severely decreasing F prime C of the concrete. Now, you have to always be aware that during the placing and dropping the concrete, those practices will basically alter the air content. The air content that is important is the air content that is in hardened concrete, but unfortunately, it is measured during the plastic state. Now, again, you have to be very, very careful about this. Provide the range for this and be a little bit more conservative over here. Another thing that I would specify I would mention over here is that the mixing also alters the air content. So I will stop here, and I will be back very soon with another lecture to cover the rest of the steps.